Hi everyone. This lesson is about proof by contradiction. Now before we get into the example of a proof by contradiction, I just want to cover a couple of fundamental ideas that we will need to use. The first is when we multiply an even number by an even number. Now if you think of a few examples, 2 times 4 is 8, 6 times 8 is 48. You will soon come to the conclusion, I hope, that an even multiplied by an even always gives an even answer. One way I could, I suppose, illustrate this is if I take, let's make it a rectangle. The two even numbers don't have to be equal. So this edge of the rectangle was an even number, so it'll be 2 multiplied by some other number. And this edge is an even number, 2 multiplied by some other number. So if I was to break this up into little groups, each of these little steps would be 2. And if I was to break this up, each of these little steps would be 2. And so each little square then is 4. Clearly that's an even number. And the whole thing is going to be made up, no matter how far I have to go this way and how far I have to go this way, it's going to be made up of little squares, which are 4s, and every one of those can divide by 2. Every one of those is even, so the whole thing is even. So that's a little visual reminder. Why did I put an N there? I had intended that to be a different letter, and I suppose I should say that both N and M are integers, because otherwise we get fractions and it gets messy and so on. How about an even times an odd? Well, let's think about that for a second. We could use our diagram again, couldn't we? So we'd have 2n, so we'd break this up into 2's all the way along, but then if it's an odd number, there would be a little 1 extra at the edge. This is an even number, so we'll break that up into 2's. So that's a 4. They're all of those are 4's. All of those are 4's all the way along, etc. Now what are we going to get over here? Well, that's 1, but that's 2. So that little bit in there is equal to 2. And then that's 2 and that's 1, so that little bit there is equal to 2, and that'll be neatly all the way down. So you've got lots of squares which are equal to 4, they're even, and you've got lots of 2's, they're even. When you add even numbers to even numbers, it stays even because they're jumping up by 2's, aren't they? So that one is also even. That's interesting. Now the last one, odd times odd. Just clear a bit of space there. If it's odd multiplied by odd, I'll try to do a slightly easier diagram this time. So an odd number is an even number plus 1. So I'll just do that down there. And this is a different odd number down the side. And of course that's a different sized even number plus 1 at the bottom. Well, what's this little bit up in here? This bit, that was supposed to be a highlight pen. This little bit up in here, well, that's an even times an even. And we've already seen that that's even. This bit's an even number. Here is an even number times 1. And here is an even number times 1. Well, that's the second example, so those bits are also even. So far we're adding 3 even numbers, it's an even number. But this last little square in the corner is a 1. And if we add 1 to even numbers, we get an odd number. So these are our little preliminary ideas that we need before we get into our proof by contradiction. And we'll be using those results in a moment. Just clear a bit of space here. Okay. So this is our proof. We are required to prove the square root of 2 is irrational. Now the way we do this, there's 3 main steps to a proof by contradiction. First, we assume the opposite statement. The opposite statement would be assume root 2 is rational. In other words, root 2 equals some number a divided by some other number b. A and b are both integers. I suppose we should specify that b does not equal 0. That's pretty important. And I'm also going to specify here that a and b have no common factor. And that's true for any ratio. We can cancel down. A and b have no common factor. Now let's see where this idea leads us. If root 2 in fact is able to be expressed as the ratio of 2 numbers, well, we should be able to make some conclusions. Let's square both sides. And let's express a squared then as 2 times b squared. Now, 2 is an even number. B squared could be anything, even or odd. But as we've just seen up here, even times even is even times odd is even. So it doesn't really matter what b squared is. We can claim that a squared is an even number because it's a multiple of 2. And a squared, well, a times a has to be the same. It's either a is perhaps even times even is even. It could not be that a was odd, because odd times odd is odd. We know that we have something by itself is even. The only way that could happen is if a is also an even number. That's the first part. Well, if a is an even number, we could express a as a multiple of 2 times some different number. Again, this different number would be an integer. Now I'm going to substitute that back into the version of a squared equals 2 times b squared. So 2 times p squared equals 2 times b squared from that top line there. Well, that's 4p squared equals 2b squared. Cancelling down, I have 2p squared equals b squared. Well, that means that b squared is a multiple of 2. So b squared is an even number, and as we saw a moment ago, that means that b is an even number. Now this is getting a little bit to the point of being absurd. We started with the idea that a and b have no common factor, and that's perfectly reasonable. We have got to the point that a is even and b is even. In other words, they could both divide by 2. Now they can't, both the green and the yellow highlight statements cannot both be true. They're contradictory. This is the contradiction. So that's the second important step. That was supposed to be in red. Having a hard time controlling the pen here. So second step, state the contradiction. if A and B are both even, then they do have a common factor. Well, the contradictions in maths are forbidden. There must be a mistake. The mistake is right back here. The only thing that is open to question is this assumption, the assumption that root 2 is rational. Everything else that follows is 100% watertight. It must be that assumption that has caused the contradiction to appear. Clearly, that assumption is false. The assumption that root 2 is rational is false. The only other possible conclusion is that root 2 is irrational. And that's what we do as our third step. We state the conclusion. Therefore, root 2 is actually an irrational number. Meaning it can't be expressed as a ratio of two integers. It would be a decimal that runs forever with no repeating pattern. Okay, that is proof by contradiction. I've taken a fair while to go through this. Take it slowly, think deeply, and above all, enjoy your maths. Thanks for watching.